Today we're going to talk about powers of complex numbers using a new theorem called the Moivre's theorem. And so powers of complex numbers are like taking a complex number to the first, second, or third power, or perhaps to a fractional power, so like taking a cube root or a fourth root or something. So in order to do this, what we would do is we could use the regular complex form, so like 1 plus I squared. I could rewrite it as 1 plus I times 1 plus I, and then multiply it out. This one isn't too bad because the numbers are very easy. So I use the distributive property. I squared is -1. 1 cancels with this -1, and I end up with 2I. So notice that 1 plus I squared is, or 1 plus I, the quantity squared, is 2I. But that gets really complicated once I get 1 plus I to the 8th or 10th or 12th or 17th or something like that. That would be a lot of distributing, and we don't really want to deal with that. So what we're going to do is we're going to use the polar form, which will help us out a lot. So clearly, if 1 plus I is just 1 plus I can write it with its radius and its angle. What we learned in the last video is that if I have a complex number multiplied by a complex number, I just take the radii and multiply them together, and then I add the angles. So if I have 1 plus I, the quantity squared, that's like saying this number multiplied by itself. So I take the radius times the radius, and then I do the angle 45 plus the angle 45. So I end up with 2 cosine 90 plus I sine 90. Since cosine 90 is 0, sine 90 is 1, I end up with the exact same answer that I said I was going to get when I multiplied it together in regular complex form. Now when I do this with 1 plus I to the third, I just multiply the radii 3 times, the radius 3 times, and then add the angle to itself 3 times. So I end up with 2 root 2 times cosine 135 plus I sine 135. So I end up with, since cosine 135 is negative root 2 over 2, and sine of 135 is positive root 2 over 2, I end up with -2 plus 2I. And I can do this much easier than doing the rectangular form of 1 plus I to the 8th. So if the original angle was 45, I just multiply that by 8 and get 360. If the radius was root 2, I take that to the 8th power because I'm multiplying it by itself 8 times. So I end up with 16 times the cosine of 360 plus I sine 360. Now, I can't write this as 360s. I would have to write them as 0 because I want my angles to be between 0 and 2 pi if I'm doing it in radians, or 0 and 360 if I'm doing it in degrees. So because of that, I would have to write 16 times the cosine of 0 plus I sine of 0. If I wrote this in regular complex form, cosine of 0 is 0, or I'm sorry, it's 1, sine of 0 is 0, so my answer is just 16, which would be the point 16 comma 0 on the coordinate plane. So that's kind of why all this works. And so if we take a look at the general form, if the radius is a squared plus b squared and theta is the arctan, I can get r to the n times cosine of n theta plus I sine of n theta. So notice that I multiply r by itself as many times as I need to, and then I just multiply theta by the power because I add the angles that many times. So here's some practice. this, number one, I would find that the radius is 2. I plotted it on the coordinate plane. And then theta is negative 30 or positive 330. I'd probably choose negative 30 to do my calculations because 30 times 9 is a lot easier than 330 times 9. But then I do 2 to the 9th because the radius is 2 to the 9th power. Then I multiply 30 by 9, so I get negative 270. And then I just have to rewrite my answer with a positive angle between 0 and 360. It tells me to leave my answers in complex form, not polar complex form, so I guess this is my polar answer, but if I want it in regular complex form, which is what the directions say, I guess this would be my answer. I misread the directions, and I have to make this video very fast because my wife is about to go to the hospital. So number 2, not for anything bad because my baby is about to be born pretty soon. 1 minus I to the 6th power. We find the radius to be root 2, and then we find theta is 315. We can do that using arctan if we want, or we just know that this is a 45, 45, 90 triangle. Then we do root 2 to the 6th, which is 8, and then cosine negative 270 plus I sine of negative 270. We get the angle in the correct order. Then this is actually the answer in polar form. I also wrote it as a point. Numbers 3 and 4 are similarly here. And I'm going to circle the actual answer that I'm supposed to have according to the directions. But radius is 2 here. Angle is negative 60. I'm probably going to use the negative 60 just because it's easier. And then I'm going to change it to 120 if I was asked to write the answer in polar form, polar complex form. But 2 to the 4th and then negative 60 times 4. Then I can convert this into the form I need. This one has a radius of 1 and then angle of negative 120. I can multiply 120 by 3 and get 360, or negative 360, which then goes to 0. 1 cubed is 1, so I could put a 1 on the outside if I wanted, but I don't really need to do that. There's my answer. There's my point. Now, if I did roots, that's like saying 1 plus I or something to the 1/4 or 1/5 or whatever. So that's kind of the same concept. And the similar concept applies. So what happens is I'm going to take this number to the 1 over n, and then I'm going to divide the angles. So notice what happens here. I take my radius, I take the cubed root of this because it's asking for the cube root. Radius of 16, 4th root, I take the 4th root of it. 243, I take the 5th root, so the 5th root of that would be 3. So notice what's happening to all of those radii is that you're just taking whatever root it is, and then for the angles, you divide. 120 divided by 3 is 40. 300 divided by 4 is 75. 90 divided by 5 is 18. So you can easily get these angles. Now, there are exactly, remember when you take a cube root or a square root or something in the real numbers, you only get one answer. But in the complex plane, we can get as many answers as the power of the root. So the 4th root, you're going to get 4 answers. The cube root, you're going to get 3 answers. The 5th root, you're going to get 5 answers. And they're all equally spaced angularly around the pole. And so, for example, on this first one, if I have a radius of 2 and an angle of 40, I'm going to have 2 more equally spaced. So this would be an angle of about 160. This would be an angle of about 280. And they're all radius 2. So what ends up happening is you have something that kind of looks like an equilateral triangle for a cube root. For a 4th root, it's going to look like a square. For a 5th root, it's going to look like a regular pentagon if you plotted all those points. So we have all these other angles that show up that are equally spaced. So the angles are equally spaced by doing 360 divided by the number of the root. Here's another example. So if I find the radius of this is like a 30, 60, 90 triangle. So I get an angle of 60. I'd get the radius of 27. I do 27's cubed root to get 3. Then I divide 60 by 3 to get 20. Then in order to get the other angles, I add 120 because 360 divided by 3 is 120. So I add 120 as many times as I need to in order to get as many roots as I have to get. So here's the general formula. It's r to the 1 over n, or you can also write that as the nth root of r, times cosine of theta over n plus I sine of theta over n. And then remember there are n roots, so you add 360 over n until you get them all. Here are the complex roots of the following things. So -1 plus root 3i. If the radius was 2, you have to take the cube root of that. So you have the cube root of 2 for all of them. Then here's your angle. So if I plotted -1 root 3, it's going to be at a 120-degree angle with a radius of 2. I divide this by 3, and then I add 120 as many times as I need to in order to get the answers. We're going to leave these in polar form, at least the first two, because they're really nasty. 3 and 4 you can convert to regular complex form because they're pretty easy, but these are nasty. And notice the picture, it looks like an equilateral triangle. These are all radius cube root of 2. The fifth roots of this, if the radius is 4 root 2, if I take the fifth root of that, I just get the square root of 2. And so I have square root of 2. The angle was 225, so I divide that by 5 because it's the fifth roots, and I get 45. Then I have to add 72 a bunch of times because 360 divided by 5 is 72. Add 72 until I get 5 whole roots. Notice it looks like a pentagon. Cube roots of -i. The radius is 1 and the angle is 270, so I divide 270 by 3. The cube root of 1 is just 1. So I have cosine 90 plus I sine 90. Then I add 120 twice because 360 divided by 3 gives me 120. So that's why I end up with these three. And notice that since these angles are nice, I might be able to convert them into regular polar or regular complex form. So the directions might tell you to do that. Fourth roots is 16. Here's my angle and my radius. So 0 divided by 4 is 0, and then I add 90 every time because 360 divided by 4 is 90. So I add 90 every time, and then the fourth root of 16 is 2. So that's my radius, and notice here's my picture, which looks like a square tilted on its side.